All right, so let's look at I guess the next topic, and we're going to be looking at the different types of possibilities as it relates to solving a system with three variables now. So when we talked about a system of equations, the first thing we did was talked about if it was only with two variables, and when that was the case, we were just basically considering the possibility that it was just two lines. So essentially, something like that, where you got two lines, and we were interested in that. So that was one solution, one point of intersection. And you didn't always necessarily have a solution because you could get the possibility where if the two lines didn't intersect at all because they were parallel, that would be no solution. And then you had a possibility where when I drew it, you only saw one line, but we were saying that they were two lines. And the way we wanted to think about it was that if it was like one line directly on top of the other one, so then all the points of intersections, well, since it's technically touching everywhere, it was infinite. So this one had one solution, this one had no solution, and this one was infinite. So if it's three variables, very similar thing is going to happen, except that now they're not going to be lines anymore. So if it's two variables, it was a line. If it's three variables, so in other words, x, y, and z, three variables, it's going to be a plane. So no longer a line, is going to be a plane. So again, I'm not a very good artist, so a plane, something like that. Okay. So then every equation is going to be a plane. So we're looking at three planes at the same time. So if that's the case, what are the different things that could happen? Well, one solution, that's a possibility, infinitely, and no solution. So the same three possibilities essentially. Now, how do we know which is which? Well, here we can look at the little picture, and the book does a very good job. So right here, there's three different planes. If you look at it, it's three different colors. And in this case, they touch at only one point, and it's the points that is right smack in the middle. So in other words, that guy right there. So there's only one solution. All right, well, the next one is that all three also intersect at the same time. But then when they intersect, it's not really a point, it's a line. So if that happens to be the case, then the points of intersection are all of these. So in other words, the intersection is a line, and a line is infinitely many points, right? So this is also considered to be infinite solutions, a bunch of points. Okay, what else? Well, you only see one plane. Well, why is that? Well, going back to the idea where when you only saw one line, and it was technically two lines, right? So where I did like that, and it was line number one, line number two, and it was touching because it was right on top of each other. Same thing with these. These are the planes exactly on top of each other. So where do they intersect? Well, everywhere, right? So this is also infinite. And the last possibility, well, the last two possibilities. Looking at this one, even though they intersect each other, it has to be all of them at the same time, at the same place. Well, that's not happening here. So, because it has to be all three, not just two. So, in this case, if you say, well, what about that? Well, that's only two at a time. What about this? Only two at a time. Only two at a time. So, there's nothing that is all three at the same time. So, for that reason, no solution. And then we can even see the last one down here. These are all parallel. So they don't touch at all. So again, no solution. All right, so now we know that these are the things that could happen. But the picture is the one that's telling you what's going to happen. What if you don't have the picture? How are we going to know which is which? Well, it has to do with when you solve it, what does your answer look like? And there's two different ways to solve, two different ways that I've showed you: Gauss, Jordan, and Gauss elimination. Okay, so let's say here you go. Here's a good example. So you have three equations, three unknowns, three equations. So we're looking for x, y, and z. You start off with three equations, but then you start doing the work, and then you get a pretty weird looking answer. And it's weird because what happens towards the end. So if we think about it as a matrix, it would look like this, right? So as a matrix, it would be 1, 1, minus 3, and minus 1. And then it would be a 0 there. 1, minus 1, 0. And then it would be a bunch of zeros all the way across. So remember that when we were doing Gauss-Jordan, what we wanted to happen was 1, 0, 0, 0, 1, 0, 0, 0, 1. And if it behaves nice like this one, automatically you get your answers. The answer that is in the blanks, I guess I'll put it in blue. That's the answer for X, the answer for Y, the answer for Z. But here, the weird stuff is happening right there, right? So it says 0 equals to 0. Well, that's a true statement, by the way. So if you do Gauss-Jordan or Gauss elimination and you get this weird looking equation at the end, but it happens to be a true statement, this is telling you that you're going to have infinite solutions. Okay? So infinite. Now, if you're going to have infinite solutions, we have to provide a general solution. General solution is kind of like a formula version, a formula that can give you all the points that are possibilities. Well, not possibilities, that are actual answers. So you would have to take it a step further and give a general solution. All right, so how do we do that? Okay, so if you notice that since the third equation was 0 equals to 0, that basically reduces down to only two equations. So if it's two equations and I need to get three answers out of it, how am I supposed to accomplish that? Well, let's take a look. Okay, so let's change the color. Here we go. What we really need is to have x equal to something, y equals to something, z equals to something. And the one that is missing, because the last equation went away because they were zeros, was where we would expect to have z. So at this point, what you do is you set z, which is a dependent variable, and you set it equal to some variable, some different variable, a different letter if you want. And you can choose whatever you want. In this particular example, they're using the letter A. And A is representing a number, a real number. So then all you have to do is, you can always do it this way. Set it equal to A. And then we can start working backwards, because the next equation, this equation right here, so I'll call it equation number 2. If you solve for y, you get that it's equal to z. In other words, you're just jumping it over. Well, what is z equal to? Well, z is equals to a. All right. So far so good, because it has to match the way we want it, where it's x equal to something, y equals to something, z equals to something. The only one that's missing is equation number 1. So if you solve that one for x, throw everything to the other side, right? Well, that's going to be negative y. If you jump over with the negative 3z, it becomes a positive 3z. And then there was a negative 1 there. Whoops. Negative 1. Let's, come on, eraser. Negative 1. But guess what can happen here? We know the number or the variable that we're using for each one. This is a, and so is this guy, that's a. Where do I get those from? From over here. So you can simplify it. So if what we're gonna get here is negative a plus 3a minus 1, that is gonna give you, if you do the work, 2a minus 1. So over here it's gonna be 2a minus 1. And now you have it in the format of x equals something, y equals to something, z equals to something. And guess what? That's that guy right there. So that's how they did it. So this is called the general solution. General solution. Okay, and when do you have to provide a general solution? If it's infinite solutions, if that's the case, that you got this weird looking answer where basically one of the equations went away, but you get a true statement. The last equation was 0 equals to 0. Okay. Let's see what else. Oh, I remember. What if there's no solution, right? What does that look like if there's no solution? And I believe it was up here. Whoops. Notice that it looks very similar. And in the last equation, you get something that is false. Right here. So the other one, we got something that was true, and this one we got something that is false. So that means that there's no solution. That's called inconsistent. All right, so that's basically how you can tell them apart. Whether you use Gauss-Jordan elimination or Gauss elimination, if you get a weirder looking answer at the end like this or like the other one, now you know which is which. Okay, so I think that takes care of that last piece of information. Now we can move on to matrix operations. Matrix operations is going to be section 8.2. So what we did was basically finish 8.1, and now this is the beginning of 8.2. All right, let's see if I can make it a little bit thicker. Okay, so we said, whoops, come on, buddy. Section 8.2, and these are called matrix operations. Well, what kind of operations? Well, the typical ones. Add, subtract, multiply, but be careful with divide. Divide misbehaves. Troublemaker. So that one requires its own special thing. The rest is actually going to be pretty straightforward, very easy. So the good news is we got the hard stuff out of the way. So now the easy part, adding, subtracting, and multiplying, is going to be pretty much a piece of cake. Okay, so here we go. Let's say, starting with a matrix, we already pretty much have an idea what a matrix is, but now we can be a little bit more detailed. Give more, fill in more of the pieces. So let's see. Okay, I don't know why it highlighted. There we go. So this is a matrix. And I'll just make up some numbers. It's not really too important. 0, 1, minus 5, 3, 7, 13, 11, 8, and 5. These are going to have their own name. So the ones that are sideways, these right here, they're going to be called rows. Row number 1, row number 2, row number 3. Compared to these, the ones that are up and down, they're going to be columns. So this is going to be column number 1, column number 2, column number 3. So then if I want to specify a location of one of these numbers inside, so the numbers inside, they're called entries. So the specific entry, if we want to talk about its location, since this is capital A, the entries we use lowercase a, and then there's going to be two numbers, I and j. So I is talking about row, J is talking about column. And you're going to see that it's always describing row first and then column second. So then this, where is it located at? Well, this is the second row and the third column. So then we write it as 2, 3. Okay, so those are called subscripts. The subscripts tell you the location. Okay, the other thing that is important is the size. All right, so the size of the matrix are given by the dimensions. So the size is given by the dimensions. What do I mean by dimensions? How many rows does it have? How many columns does it have? And like we said, rows goes first and columns go second. So how many rows does this thing have? 3. How many columns does it have? 3. So what's the size of this matrix? Well, it's a 3 by 3 matrix. Okay, first definition, equality of a matrix. Equality. So if you have that matrix A equals to this other matrix B, what are the conditions that it must satisfy? Again, this is going to be kind of common sense, but it's good to just point these out specifically. It has to have the same size, right? They both have to have the same size. Same size, which means the dimensions. Okay, number 2. It has to have the same things inside, the same numbers. We said they're called entries. So corresponding entries are equal. All right, so it looks like this thing decided to quit on me. Let me try it again. All right, let's give it a try. There we go. Entries are equal. Okay, so then we can do a quick example. And we have 2 different matrices. Well, different name. They're supposed to be equal. So this is going to be 7, 9, and X. Negative 2Z, I'm sorry, 2Z. Negative 1 and 11. All right, what about this other one? 7, 9, 0. 4 minus 1. And then Y plus 1. And we need to find X, Y, and Z. X, Y, and Z. Well, this should go pretty smoothly because this is located in the same as this one. So those are considered to be corresponding entries. So that gives you the first answer, X equals to 0. And then we can say that, well, I'll use a different color. This one goes with this one. So then 2z equals to 4. Divide both sides by 2, so z equals to 2. And then the last one, this goes with this one right there. So then I have y plus 1 goes with 11, minus 1, and you get a 10. So not bad at all. Pretty easy, like I was saying. Most of this stuff is going to be very straightforward. Okay, let's keep going. So now, if we consider a matrix is built from a bunch of small matrices. So I like to think of them as the building blocks, the basic types of building blocks. Okay, building blocks. The first one is going to be called a row matrix. Then it's going to be called a column matrix. Then it's a square matrix. And it's going to be very easy to know which is which. Actually, common sense again. So let's say, starting off, if I call this first one, give it a name, A. And these are the numbers. Again, I'm just making up numbers. 5 and 3. What about this one? Let's say the numbers that go with it. 0, 4, 1, minus 5. And what about this last one? 1, 0, 0. Well, let's say 1. And 0. Yeah, that looks better. Obviously, this is only containing a column. Columns are the ones that go up and down. Rows are sideways. So this is a column matrix, right? Column matrix. Row matrix. And that's a square matrix. Well, if it's a matrix, we can say what's the size. So then let's describe the size for each one. The first number is for rows, the second number is for columns. How many rows, how many columns? Well, we know it only has one column, the one that goes up and down. But technically speaking, a row could just have one number by itself. That's totally okay, that's legal. So if that's the case, this is considered to be a row. That's a row, that's a row. So then this is 3 rows, 3 by 1. Okay, what about B? Well, it's only 1 row, but how many columns? Again, a column can have a number by itself. So if that's the case, every number by itself is going to be a column. 1, 2, 3, 4. 4 columns. A 1 by 4. This one has 2 of each. 2 rows, 2 columns. Alright, so those are the building blocks. Now, the first operation is adding and subtracting. And the good news is we can do them together at the same time. I guess let's do a mini definition. How to add. And we said we do it at the same time. Subtract. Okay, so if that's what we're going to do, we just need to make sure that they have to be the same size, whatever it is that you're going to try to add. Matrix has to be added with another matrix that is the same size. And then how is it that you're supposed to add or subtract? Corresponding entries. In other words, match the numbers. And it'll be pretty easy. Okay, so let's see it in action. Let's call this matrix A. And we're going to add it with matrix B. Again, I'm just making up some numbers. So you just have to match them up. And if it's telling you to add, you add them. If it's telling you to subtract, you subtract them. So in this case, it wants us to do addition. So since we're adding, this guy here matches up with this guy here. So those are the ones that you add to get the first answer. That is a -2. And then if you do the next one, that one matches up with that one. 2 plus 1 is 3. And you just do that with the rest. -3 and a +2 is a -1. -1 and a -2 is a -3. 0 and 7 is 7. 5 and 0 is 5. Pretty straightforward. Now, it worked out nicely because they were the same size. This has 3 rows and 2 columns. So does this guy. 3 rows, 2 columns. If they weren't the same size, this wouldn't be possible. So you can see why it is that that condition has to be in place. Let's see what would happen if they happen not to be the same size. So let's say, what if? So this one is gonna be 1, 5, 2, 0. And I'm gonna try to add it with 0, 3, 6, 1, 4, -2. Well, it turns out that everything matches up nicely except these are extras. So nothing is gonna match up with those. So if it has nothing to match up with, that means you can't add or subtract for that matter. So in this case, it's not really possible. And some people just say that this operation is undefined. So whichever one you prefer, I think this book says not possible. So if you're gonna do it on WebAssign, one of the answers would just be type in not possible. So adding and subtracting is a piece of cake. Next is multiplication. There's going to be two types of multiplication: scalar multiplication and matrix multiplication. Scalar multiplication is, if you think of it as distributing, then it'll be very straightforward to do it since everybody knows how to distribute. Scalar multiplication. And then there's another concept that is called transposition. So let's start with scalar multiplication. So if you've ever taken a physics class, you've heard this word before, a scalar. Scalar basically is referring to a number. So scalar multiplication is a number times a matrix. So it's a number times a matrix. And how is it that you're supposed to do this operation? The number gets multiplied with everything inside. In other words, the distributive property. Okay, number 2. What about transposition? How does that work? Transposition is going to tell you to switch. The rows are going to turn into columns and vice versa. The columns are going to turn into rows. So this is simply switching rows and columns. Okay, so let's do one that has a little bit of everything in it. Oh, by the way, I forgot the notation. It looks like a little exponent. So T stands for transposition, and it is written like an exponent, even though it's not. But that's the way it works. That's the notation. There you go. A little bit of everything. This is a negative. It's going to have scalar multiplication, which is essentially that guy right there. And it's going to have transposition, which is that guy right there. All right, so scalar multiplication tells you to multiply by distributing every number inside. So multiply everything by -2 inside. So this is times 1 is -2, times 5 is -10, times 3 is -6, -16, +14, and -4. And then after that, we can take care of transposition. Transposition, the rows are going to turn into columns. In other words, this guy is going to be switched. Now it's going to go this way. Right? So it'll be like -2, -10. And then if you do that to all of them, -6, -16, 14, -4, and there you go. So that's the result. Okay, what about division? Would it be legal to try to divide? Let's say we had 0, 3, 6, 12 minus 3 and 2, and you wanted to divide everything by 3. Is that legal? Well, we didn't explicitly talk about division, but division is a form of multiplication. You multiply times the reciprocal. So technically speaking, it's the same thing as saying 1/3 times the matrix. So guess what? That's scalar multiplication. So yes, very much legal. So it's really the same thing, multiply times everything inside, or divide by everything inside. So if you think of division, 0 divided by 3 is 0. 3 divided by 3 is 1. 6 divided by 3 is 2. 12 divided by 3 is 4. -3 divided by 3 is -1. 2 divided by 3, it doesn't reduce, it's actually a fraction, 2/3. And yep, totally possible. Okay, so now that we have all the definitions in place, now we can do a little bit of a practice problem. All right, A. So in this example, they're going to give you A separately and B separately, and then we have to do the operation that they're asking. 1, 0, 3, and -2, 1 and 5, and then B, 2, 0, 1 minus 1, and then 3 and 4, and this is the calculation. B transpose minus 2 times A. So what does that equal to? Well, we just have to plug in the matrix. Matrix B goes in there, matrix A goes in there. Okay, starting with B, bring it over, right? As a T there, -2, and then A is gonna go over here, right? All right, plug in all your numbers. We already know what T stands for. It means swap things around. This row is going to turn into a column. Okay, so switching things, you're going to get 2, 0, 1 minus 1, 3 and 4. No, what about this guy right there? Multiply everything by 2. So do I multiply everything by 2 or everything by negative 2? Well, if you multiply everything by negative 2, that means you have to include the negative. So this answer will be added. If you're not going to do negative 2, then you have to bring the negative. Oops. Bring the negative and then use positive 2. So I guess that I'll do it that way. They're both correct. So this is 2 times 1 is 2. 2 times 0 is 0. 2 times 3 is 6. Positive times a negative is a negative 4. A positive times a positive is a 2. 2 times 1 is 2. Positive and a positive, 10. And then remember what we said. This goes with this one because they're in the same location. And if it's telling you to subtract 2 minus 2, that's 0. And then that one goes with that one. 1 minus 0 is going to be 1. And then you just go all the way with the rest of them. 3 take away 6 is negative 3. 0 minus minus 4. Negative negative turns into a positive. 0 plus 4 is 4. Negative 1 minus a 2. That's a negative 1 and a negative 2 is negative 3. And the last one, 4 minus 10 is negative 6. Okay. So, as long as you understand the little rules and you're careful about it, it shouldn't be very hard at all. So this is way easier compared to Gauss elimination, Gauss-Jordan. So we got the hard stuff and we got it out of the way. So I mean, we did the hard stuff first to get it out of the way. So whatever is left is way easier in comparison. All right, let's solve a matrix equation. Solve for x. But notice I'm going to make a capital X because x is not a number. X is a matrix. So we're going to solve for a matrix. That's called a matrix equation. All right, this is what it looks like. Capital X. So remember, if you use a capital letter, you're talking about a matrix. If you use a lowercase letter, it's an entry. Entry means it's a number that is inside of a matrix. Okay, so we're all set. We're going to solve for x. So a little side note. Think of it like if it was just a regular equation. What would you do if it was a regular equation? If it was 2 minus x equals to 5, you would minus 2 on both sides, right? That would cancel. Negative x equals to 3, and then you would divide both sides by negative 1 because that cancels and then equals negative 3. So you want to use a similar type of idea, just as long as you're following the rules for a matrix. Okay, so with that in mind, multiply the 2 first, and then we'll subtract it from both sides. So that's going to be a 2 times 1 2 times negative 5 is negative 10. 2 times 2 is 4. 2 with 0 is 0. And then nothing happens over here yet. If you subtract it to both sides or just move it over, let's just move it over so it doesn't get too ugly. So it's nice and clean. When I move it over, so I'm going to put it on this side, right? 2, negative 10, 4, and 0. But it's going to be the opposite sign. In other words, it's minus. So that's telling me that I'm supposed to subtract. Going back to the way it works, that this goes with this, and you're supposed to do this. Negative 6 minus 2 is a negative 8. And then this guy goes with this guy. 5 minus a minus 10, that's a plus 10, so that's 15. And do that for the rest of them. 9 take away 4 is 5. 1 minus 0 is 1. Lastly, divide both sides by negative 1. And we said, yes, that's legal because you're dividing by a number. And it's technically scalar multiplication. Distribute, negative, negative, positive, positive, negative, negative, positive, negative, negative, positive, negative, negative. And that's your answer for matrix X. So as you can see, everything has gone very smoothly up to this point. There's only one operation that is slightly more difficult. Not that it's very difficult. Compared to everything else, it's a little bit longer. So I said that there's two types of multiplication: scalar multiplication and matrix multiplication. So the one we've been using is scalar multiplication, which is a number times a matrix. Very easy, you just distribute the number. Matrix times a matrix is a little bit more involved. So to make it easy, let's go back to the building blocks. Which is a row matrix and a column matrix. So it's called row column multiplication. Row column multiplication. Instead of trying to write the definition, it's just easy if we do an example because it's very easy to follow what the pattern is going to be. All right, so let's just make up some numbers. That way we can follow along and see the pattern. So let's say that's my row matrix. And then we need a column matrix. So what do you do? Well, what we're going to have to do is multiply, because it's called multiplication. So you just go in a specific order. The row matrix goes from left to right. The column matrix goes from top to bottom. And you're just going to match them up. So I'll use colors. The first one here goes with the first one here. The second one goes with the second one. The third one with the third one. And you get the idea. The fourth one with the fourth one. So those match up. So all you have to do is multiply and add at the same time. So let's take care of it. 3 with -2. 3 with -2. -1 with -1. -1 with -1. 0 with 4. 0 with 4. And 5 with 3. 5 with 3. So you add your answers. Well, this is a -6 plus negative a negative is a +1 plus that's a 0 plus that's a 15. So what do we end up getting? You end up getting a 10. Okay, so there's only one thing that's missing. Part of the definition is that a matrix times a matrix, the answer is supposed to be a matrix. That means that the only thing that's missing is write it inside a matrix. And that's it. Well, if this is a matrix, what is the size of this matrix? Remember, we were giving the dimensions. How many rows, how many columns? Well, this is considered to be a 1-by-1 matrix. It has one row and it has one column. So here's where something special starts to happen with multiplication. If you look at the dimensions, the row, it was 1 by 1, 2, 3, 4. This one was 1 by 4. One row, 4 columns. This one has 1, 2, 3, 4 rows and 1 column. And something special here has to happen. These numbers in the middle, they have to be equal. And if those numbers in the middle are equal, then the numbers in the outside tell you what the result has to be. So the result is going to be a 1-by-1 matrix. Yep, that's exactly what happened. What if the middle numbers are not the same? Well, if the middle numbers are not equal, then it's not possible. It's not going to work. Okay, so this is an example of a row times a column. When we think of matrix multiplication, it's all the building blocks put together. So you could have a bunch of rows with a bunch of columns. So it sounds complicated, but just as long as you're careful and keep track of what's happening, it's not going to be too bad. All right, so let's make it official. Matrix multiplication. All right, let's just make up some numbers here. So 1, 2, 0 minus 3. And let's say this is going to get multiplied with 3 minus 1, 5, 2, 7, 0. Now let's just map it up so we can see exactly what's going to happen and we don't get confused. So it has to be a row times a column. So let's write down the rows on this side, row 1, row 2. and it has to be times a column. So this guy over here has to have columns. Column 1, column 2, column 3. All right, so let's map exactly what's going to happen. Remember that certain numbers have to be the same for this to work. This is a 2 by 2 matrix. This is a 2 by 3 matrix. And not only do the middle numbers have to be the same, right? They have to be equal. But the outer numbers are going to tell you what the result is going to be. So my result is going to be a 2 by 3. So if it's a 2 by 3, well, let's do it this way. That means 6 slots or blanks. That's a 2 by 3. Now we have to fill in the blanks. So this is where we're going to map it out so we can see exactly what's going to happen. Remember that I said that rows go from left to right, columns go bottom to top. So the first one is going to be row 1 with column 1. Row 1 with column 1. And then it's a repetition, row 1 with the next column. R1 with C2. Then it's the next one. R1 with C3. And you just repeat the process with the next row. R2, C1. R2, C2. R2, C3. Now we just have to calculate what these answers are going to be. So we just mapped it out so we know exactly what goes where. Now it's just time to do the calculations. All right, so when you do row 1 with column 1, it's going to be, let's use a different color. The first one with the first one, and then it's, let's see, what other color do I have disposable? The second one with the second one. So it's 1 times 3 gets added with 2 times 2. In other words, it's 3 plus 4 is 7. Okay, let's repeat it with the next one. The first one with the first one. The second one with the second one. But which one are we using? This first one with this first one, this second one with this second one. Because it says R1 with column 2. So this is R1 with column 2. So the way I kind of like to think about this is, it's like if you distribute. Let me make some space here, so I can put my little arrows. I think of it this way. This, oops, come on, buddy. This one there, then there, then there. You distribute. All right, so we're here. The first one with the second one. The first row with the second column. So it's 1, negative 1. So that's negative 1. And then if you want, I can even put the work over here on the side. So it was 1 and 3. So it was 1 and 3. And then it was 2 and 2. 2 and 2. And that was 7. So that was this first answer. And then when I move on to the next one, it's going to be the 1 and the negative 1. And then the second one with the second one, the 2 and the 7. So that's 14. Take away 1, it's 13. All right, now it's row 1, column 3. 1 with 5. So the first one with the first one, the second one with the second one. 1 with 5. And then it's going to be 2 with 0. So that's a 5. Right, and then you just keep going like that. Now we repeat the same process but with the next row. Okay, so it's going to be the first with the first, the second with the second, 0 with 3. So I'll write them down for you again. 0 with 3 plus negative 3 with 2. So that's going to be negative 6. Okay, what about who's next? Now we're over here. This one with this one. The first one with the first one, so 0 with negative 1. Negative 3 with 7. So in other words, negative 21. And the last one. 0 here with 0 here. Negative 3 here with 0 here. So just by looking at it, it's a 0 with a 0, but I'll write it down. 0 with 5. And then negative 3 with 0. That's why that's going to be 0. And that's it. So that's matrix multiplication. So yes, it is technically harder than the other one, as you can see. But just as long as you're organized, it shouldn't be too bad. All right, let's see. So I'll have to give you one for practice. That's the only way you can learn if you actually do one of these. Let's say A 103 negative 2 1 and 5, and then B, it's gonna be 2 0 1 minus 1 3 and 4. Okay, number 1, multiply A times B. Number 2, multiply B times A. Now you might be thinking, well, isn't it really the same thing? Well, if we were talking about numbers, regular numbers, not a matrix, so I'll put it over here on the side for you. If you say 2 times 3, yep, that's 6. 3 times 2, yep, that's 6. So if you change the order, it's going to give you the same answer. right? So that's called the not the associative property. It's I forgot what the name of this property is, but it has to do with the order. If you change the order, multiplication still gives you the same answer. Well, is that gonna still be the same thing for a matrix? It's called the commutative property. Commutative property. Commutative property. Well, let's see. Looking at matrix A, 2 rows, 3 columns, 2 by 3. And B is 3 by 2. Right off the bat, the middle ones have to be the same in the R. The outside ones tell you what the answer is going to be because that's the result. So my result is a 2 by 2. Okay. So when I work it out, 1, 2, 3, 4 blanks. Let's check it out. What if it was in the other order, right? 3 by 2, 2 by 3. Are the middle numbers the same? Yes, they are. But what about the outside numbers? Well, this is 3 by 3. So guess what? It's not going to give you the same answer if you change the order. This is going to have 1, 2, 3, 1, 2, 3, 1, 2, 3. So matrix multiplication does not have the commutative property. If you change the order, it's a different answer. All right, so this one you need to practice on your own. Let me give you the answers so that way when you're done, you can check your work. You need to get 11, 12, 12, and 19. And if you don't get them correctly, ask me and then we can try to work on it during class. 206, 3 minus 1 minus 2 minus 5, 4, and 29. All right, now let's put these definitions together, and so we can apply them with the concept of a system of equations. There we go. It doesn't let me move it out of the way, but now it does. System of equation. All right, so let's say I have a matrix here. 1 minus 1 and 1. And then 0, 2 minus 1, 2, 3, 0. I have another matrix over here, x, y, and z. And I have another matrix over here, 3, 1, and 4. Well, this matrix is called matrix form. Matrix form. Well, this system, I should say, is called matrix form. This is called matrix A, X, B. Notice that I'm using capital letters because a matrix, the name is with a capital letter. If it's a capital letter, it's a matrix. If it's a lowercase letter, it's a number inside of the matrix, right? A scalar, in other words. Okay, well, how does it look like if it's supposed to be equation 1, equation 2, equation 3? Remember the way we were writing it? How can I write it so then it's with 3 equations? Okay, this came out kind of ugly. Let's try that again. There we go. Well, we know matrix multiplication. Rows, you go that way. Columns, you go this way. So if it's the first one with the first one, 1 times 1 is x. Negative 1 goes with y. You get negative y. 1 goes with z. You get z equals. Well, that's your equals. And it corresponds with this entry because of the location. That's 3. Once you see 0 with x, that's 0. 2 with y, that's 2y. Negative 1 with z is negative z. And that's a 1. And then the last one. 2 goes with x, 2x. 3 goes with y, 3y. 0 goes with z, equals 2, 4. So now you know how to go back and forth, writing it in matrix form. Okay, so this one is called the matrix of coefficients. In other words, the numbers in front of these. This is the matrix of unknowns. Well, how many unknowns do you have? 3 of them, x, y, and z. And then this is the matrix of constants. Which ones are your constants? These right there. All right, so that's going to take care of 8.2. So make sure you practice and take good notes, and then I'll go ahead and upload the extra credit assignment, and I'll tell you when it's ready. I'll send out an email, and it'll be posted on WebAssign.